morning. Today we are discussing about passive networks and network theorems. This is the common DC circuit. We have energy sources and resistance in it. The basic parameters of DC circuit, the mainly terms are circuit, path, node, branch, loop, mesh. For example, a circuit is a closed loop conducting a path in which an electric circuit flows in the current. Path, a single line of connecting elements or sources. Node, a node is a junction, connection or terminal within a circuit where the two or more circuit elements are connected or joined together, giving a connection point between the two or more branches. A node is indicated by dot. Node is also called a junction which has a terminal within the circuit or two or more circuit elements are connected or joined together, giving a connection between the two branches. A branch is called a single or a group of components such as resistor or a source which are connected in between two node points. A loop is a closed path in a circuit in which no circuit element encountered more than once. It is also known as a closed path of a circuit, nothing but a loop. Mesh. A mesh is a single open loop that does not have a closed path, then components inside the mesh. The mainly laws are followed by DC circuit, that means a Kirchhoff laws. In 1845, a German physicist Gustav Kirchhoff developed a pair of set of rules or laws which ideally with the conservation of current and energy within the electrical circuits. These two rules are commonly known as Kirchhoff circuit laws, with one of Kirchhoff laws dealing with the current flowing around the closed circuit. It is also known as Kirchhoff current law or current theorem. KCL, while other laws deal within voltage sources present in a closed circuit, is known as Kirchhoff voltage law. Kirchhoff voltage law, it is also called Kirchhoff voltage theorem. The Kirchhoff first law, that means a current law, states that the total current or change in entering a junction or node is exactly equal to the charge leaving the node, as it has no other place to go except to leave, as no charge is lost within the node, or the algebraic sum of all currents meet at a point is 0. The both statements are proved for Kirchhoff current law. In other words, the algebraic sum of all currents entering and leaving the node point must be equal to 0. That equal to current existing plus current entering, both are that equal to 0. This idea by Kirchhoff is commonly known as conservation of charge. Here the diagram representing arrow marks downwards the junction is now entering the current and leaving the junction, that means going to the outside. The entering the current of the node is equal to currents entering to the node. Here I1 current, I2 current, I3 current both are entering to the junction, and I4 and I5 are leaving the junction. So algebraic sum of all currents meet at a point is 0. Here the three currents entering the node I1, I2, I3 are all positive in value, and the two currents leaving the node I4 and I5 are negative in value. Then this means we can also rewrite the equation as I1 plus I2 plus I3 minus I4 minus I5 equal to 0. The term node in any electrical circuit generally refers to connection or junction of two or more current carrying paths or elements such as cables and components. We can use Kirchhoff current law in parallel circuits. One more law is called voltage law. It is also called Kirchhoff's second law. The KVL states that in any closed loop network, that the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is equal to 0. Once again, the KVL states that in any closed loop of a network, the total voltage around the loop is equal to sum of all voltage drops within the same loop, which is also equal to 0. In other words, the algebraic sum of all voltages within the loop must be equal to 0. This idea by Kirchhoff is known as a conservation of charge. Here, the diagram representing A, B, C, D terminals. In each terminal we have a resistor. The current flowing through the loop is a closed path. The sum of voltage drops around the loop must be equal to 0. A to B, B to C, C to D, D to A. That means VAB plus VBC plus VCD plus VDA, and almost voltages are 0. Next one, these laws are mainly used in mesh analysis, branch current method and node analysis method. Firstly, we are discussing about mesh analysis. The mesh current method also quite similar to the branch current method in that it uses simultaneous equations, that means Kirchhoff voltage law and Ohm's law, to determine unknown currents in a network. It differs from the branch current method in that does not use Kirchhoff current law, and it is usually able to solve the circuit with less unknown variables and less simultaneous equations, which is especially nice if we are forced to solve without a calculator. An easier method to solve the above circuit is by using mesh current analysis or loop analysis, which is also sometimes called Maxwell's calculating current methods. Instead of labeling the branch currents, we need to label each closed path or closed loop with a calculating current or calculating current. Another one, nodal analysis. The node voltage method of analysis to solve the unknown voltages at circuit nodes in terms of a system of KCL equations. This analysis looks strange because it involves replacing voltage sources with equivalent current sources. Once again, the node voltage method of analysis solves for unknown voltages at circuit nodes in terms of a system of KCL equations. This analysis looks strange because it involves replacing voltage sources with equivalent current sources. Some of the rules we have to follow the node analysis method to convert voltage sources in series with a resistor to an equivalent current source with a resistor in parallel. To change the resistor value to conductances, select the reference node, that means E0, assign unknown voltages E1, E2 and so on En to remaining nodes. Write to KCL equation for each node 1, 2 and so on n. The positive coefficients of the first voltage in the first equation is the sum of conductances connected to the node. The coefficient for the second voltage in the second equation is the sum of conductances connected to that node. To repeat for a coefficient of third voltage for third equation and other equations for some of the node points, this coefficient falls on a diagonal. All other coefficients or equations are negative, representing conductances between the nodes. The first equation, second quotient, is the conductance of first node to second node. The third quotient is the conductance from first node to third node. Fill the negative quotients for other equations. The right hand side of the equations is the current source conducted to the respective nodes. Solve the system of equations for unknown node voltage. This is the way to find the node voltages for unknown voltages. Next one, branch current method. The first and most straightforward network analysis technique is called the branch current method. In this method, we assume the directions of currents in a network, then write equations describing their relationships to each other through Kirchhoff's and Ohm's law. Once we have one equation for every unknown current, we can use the simultaneous equations and determine all currents and therefore all voltage drops in the network. Some of the steps to follow the branch current method for analysis. Choose the node and assume the directions of currents. To write KCL equation, that means Kirchhoff current law equation relating to the currents at the node. Label the resistor voltage drop polarities based on the assumed currents. Write KVL equations for each loop of the circuit, substituting the product IR, that means V equal to IR, current and resistance of the product, for E in each resistor term of the equation. Solve for unknown branch currents, that means simultaneously equations. If any solution is negative, then the assumed direction of the current for that solution is wrong. This is the main point. If any solution is the negative, then assumed direction of the current for that solution is wrong. Solve for the voltage drops across the resistors, that means E equal to IR. This was the passive elements of the networks. Next, we are discussing about the network theorems. Network theorems are classified for 6. First one, superposition theorem. Second one, Thevenin's theorem. Third one, Norton's theorem. Fourth one, reciprocity theorem. Fifth one, maximum power transfer theorem. Sixth one, Millman's theorem. Firstly, we are discussing about superposition theorem. Here the circuit representing for two voltage sources V1, V2 and current sources I1, I2 and internal impedances Z1, Z2 and Z3 respectively. Statement of the superposition theorem. In linear, active or bilateral network, current flowing through any component is algebraic sum of currents due to individual sources taking one at a time, replacing remaining sources with their internal impedances. In any linear, active, bilateral network, current flowing through any component is the algebraic sum of currents due to individual sources taking one at a time, replacing remaining sources with their internal impedances. Here the circuit representing for linear impedances Z1, Z2, Z3 and voltage sources are V1, V2 and current sources are I1, I2 respectively. Consider a network shown in the figure in which Z1, Z2, Z3 are the impedances and V1, V2 are applied sources. By applying the mathematical analysis for the circuit, we get the output of superposition theorem of each current will be the sum of individual currents of the voltage source. That means I1 equal to I1 dash plus I1 double dash, I2 equal to I2 dash plus I2 double dash. It is clear from above equation that the current flowing through any component is algebraic sum of currents due to individual sources taking on at a time. Hence, the superposition theorem is proved. Next one, we are discussing about Thevenin's theorem. Here, the Thevenin's equivalent circuit representing in the figure B and main circuit is representing in a figure A. Here figure A representing for linear bilateral active network and figure B representing for equivalent circuit. In any linear bilateral active network connected between two terminals like A and B can be replaced by a voltage source applying voltage of VTH in series with an impedance of ZTH, where VTH is known for Thevenin's voltage and is open terminal voltage across A and B terminals. ZTH is known as Thevenin's impedance and is measured across the terminals A and B by replacing all energy sources with their internal impedances. Once again, we have a statement. Any linear bilateral network connecting between the two terminals A and B can be replaced by voltage source by applying voltage VTH in series with an impedance ZTH, where VTH is known as Thevenin's voltage and is the open terminal voltage across A and B, and ZTH is known as Thevenin's impedance and is measured across open terminals A and B by replacing all energy sources with their internal impedances. Here ZTH is the internal impedance, VTH is the Thevenin's voltage, ZL is called load impedance. Norton's theorem. In linear bilateral active network connected between two terminals of A and B can be replaced by current source supplying current IN in parallel with impedance Zn, where IN is known as Norton's current and is measured by short circuiting the terminals A and B. Zn is known as Norton's impedance and is measured across open terminals A and B by replacing all energy sources with their internal impedances. Here the figure A representing for linear bilateral active network with the load impedance ZL, and IN, Zn, ZL both are in parallel combination of the terminals A and B. Maximum power transfer theorem in DC source. In linear bilateral active network, power delivered to the load is connected between the two terminals is maximum when the load resistance is equal to internal resistance of the source. That means RTH equal to RL. In linear bilateral active network, power delivered to the load is connected between the terminals. That means two terminals is maximum when the load resistance is equal to internal resistance of the source. That means RTH equal to Rin. In maximum power theorem in AC, in any active network, power delivered to the load is maximum if the load impedance is complex conjugate of internal impedance of the source. Maximum in a power of terminals A and B if the load impedance is complex conjugate of internal impedance of the source. Reciprocity theorem. In any linear bilateral active network, the voltage applied in one mesh and the resulting current in another mesh are interchangeable. That means here figure 1 shows single voltage source and the resistances are R1, R2, R3 and the current flowing through the circuits are I1 and I2 respectively. In figure 2, the currents are I1 dash and I2 dash with the voltage source of V. We generally, to prove the reciprocity theorem, we have to prove I2 equal to I1 dash. That means the second network having a second mesh of flow of current I2 must be equal to first circuit of a first mesh of a current flowing through the circuit is I1. That means I2 equal to I1 dash. Finally, theorem, the Millman's theorem. In a network, if it contains a several voltage sources E1, E2, E3 with an integral impedances Z1, Z2, Z3 and Z on, which are connected in parallel, may be replaced by a single voltage source E with internal impedance Z, where the E and Z are equal to E1 Y1 plus E2 Y2 plus E3 Y3 by Y1 plus Y2 plus Y3 and so on Yn. Here the impedance is nothing but the reciprocal of admittance. That means admittance is measured in ohm inverse, that means mhos. Admittance is nothing but the reciprocal of impedance. Consider a network containing the sources E1, E2, E3 and so on En with an impedances Z1, Z2, Z3, Z4 and so on Zn, which are connected in parallel as shown in the above figure. Finally, we have to prove E equal to E1 Y1 plus E2 Y2 plus E3 Y3 by Y1 plus Y2 plus Y3. This is about Millman's theorem. Finally, we have discussing about star to delta and delta to star conversions. Now we are going to convert star to delta conversion. We have to convert star is connected impedance to delta connected impedance. Let's derive the equation used to star to delta conversion. The given figure shows star connected impedance RA, RB, RC, while the equivalent impedance R1, R2, R3 as shown in the figure. Here RA, RB, RC are representing for star network and R1, R2, R3 are representing for delta network. After completion of the mathematical equations, we get to output of star to delta conversion. Last one, delta to star conversion. The delta connected network can be transformed into star configuration using a set of electrical formula. Let's derive the equation for each impedance. The given figure shows delta network having the terminals A, B, C with the impedances R1, R2, R3 respectively. The equivalent star connected network with a RA, RB and RC, where they are connected to their corresponding terminals as shown in the figure. As mentioned earlier, the terminals A, B and C remains same, as well as the impedance between them must remains also same. Here your left hand circuit representing for delta network, that will be changes into star network. Here R1, R2, R3 representing for delta network and RA, RB, RC are representing for star network. After mathematical inversions, the networks are changed to delta to star. Thank you.